Welcome back everybody. So today we'll be continuing simple harmonic motion, and today we'll be seeing another example of simple harmonic motion demonstration. So this is oscillation of a mass attached to a vertical elastic spring. So basically there is a spring of length L, so length is L, okay, and a mass of M. So this is a mass M hangs from the free end, so from this end, so mass is M, okay, and due to the weight of M, the length of the spring is increased by L. So suppose it is, so we are considering this is the length L, okay, and due to this weight it has gone down to length L, okay. When the mass is pulled, so now when it comes here, now we are pulling it by a distance of x, okay, and then we are releasing it. So after releasing, then it starts oscillating harmonically, okay, in vertical direction. So up and down, it goes up and down like this. And for spring there is something known as K, that is a spring constant, okay. So spring constant K, okay. Now we'll be seeing the force that is exerted by the spring. So the force exerted by the spring, that is, we are taking it at F, so that is Kx. So this is the standard formula. And now K, we'll be seeing this will be m omega square, okay, and omega square we are breaking it as m, this is m, and g upon L. So from Newton's second law, we can say that ma, that is acceleration, and we are writing in differential form. So d2x upon dt2, that is equals to minus k of x. This negative sign indicates that the force is in upward direction, because on gravity it goes down, but we are intentionally making it go up, so that is the negative direction. And from these two equations, so this is equation 1, this is equation 2, we'll just compare and give a good result. So here it will be d2, so this comes here, okay, so kx upon m, just from this equation, and this on right hand side it will be 0 because it is coming here, so it comes here, okay. Now we'll just more simplify it, so d2x upon dt2 plus omega square, k upon m we are considering at omega square, it is equals to x. So this is our differential equation of simple harmonic motion, where omega equals to root under k upon m, okay. So this is the differential equation of a simple harmonic motion, and it indicates that the motion of loaded spring is in harmonic. And finally we'll just find time period, to 2 pi upon omega. So this will be 2 pi upon root m upon k. So this was all about spring constant and oscillation that is executing simple harmonic motion. So if you had any problem, just comment below, and if you did like the video, hit the thumbs up button and subscribe to the channel for more videos. So thanks for watching it.